So hello everyone, we have today a tutorial class, okay? So I'm recording the class now, so if you see me just speak in English, so no problem, okay? So the screen is clear now. We'll do the number of tutorials, all right? So the first one will be question number 1. Okay, this is exercise 2.8 in chapter 2, page number 45. So a car of mass of 1,250 kilogram is designed to have a natural body bounce frequency, which is 1.75 hertz. Assume damping is negligible. Right? So some of these terms or statements in the question you should understand, okay? Because that one will indicate a lot of things by which it will ease your solution or the way to your solution. So the first thing is that they say damping is negligible. What does it mean? Damping is negligible. So the damping is 0, right? Damping force is 0. And damping coefficient is going to be almost 0, right? So determine the effective spring stiffness to meet this requirement, okay? So what we have in here, we have the mass, all right? So we have which is a car, okay? Car, okay, which has the body bounce, okay? This is a car which has a mass, all right? And it will have the spring which has stiffness K. All right. Then the mass is given, which is 1,250 kilograms, and the frequency or the natural frequency, as you see, it's hertz. Then it will be not angular. It will be natural, which is only the frequency, which is 1.75 hertz. And remember that hertz means 1 cycle per second. Okay, 1 cycle per second means 1 hertz. All right, if it 1.75 means 1 cycle 0.75 hertz, 1.75 cycle per second, right? So how can we find the stiffness? It's very easy. Okay, this is what we studied before in the dynamics 2, right? Dynamics 2. Therefore, we have, so we have omega naught. So this is natural. We put subscript as naught, okay? Because it's a natural. So this one is going to be 2 by f, if you remember, right? Therefore, f, okay. So omega 2 by f, right? F is given. Then omega naught is going to be 2 multiplied by 1.75 hertz. So if you multiply by, if you use your calculator and multiply 1.75 multiplied by 2, it will give you 3.5, isn't it? No, 2. And that one will be 3.5, right? Or 7 over 2. Okay, so 7 or 2 over 2 by. So what's the unit of that? Of the angular frequency. Frequency. You forgot? Radians per second, right? Radians per second. All right. Now we have the omega, right? And we have the mass. Can we find the stiffness of the spring? Huh? How can we find that? Which is the general formula for a natural or free, which is free undamped oscillation, right? What's that? Okay. Omega naught is equal to square root of K over M. Okay, this is that. formula. So, and that one will be omega naught is going to be square root of k over m. But we know omega naught, right? Therefore, k, if we square both sides, then become omega naught squared equal to k over m, right? Therefore, k will be nothing but omega naught squared multiplied by the mass. This is it's given, it's calculated, all right? Multiplied by all squared multiplied by, which is 1,250 kilograms. Can you try calculating that and let me know how much you are going to get? It will be will be 120 multiply. What you will get? Always in the tutorial you'll find the correct answer in here. Naam? How much? Yes. Very good. So this is the answer, and it's similar what's given in the 151.128 or 1.3. Okay, 1.3 or 1.13. Multiply 10 to the power 3. What's the unit, Abdullah? Newton per meter as spring stiffness. And this is the answer. Is it difficult? We just have some revisions. Yes, to refresh. As you are going forward, you will get more trained about what we have got in the previous classes. Right? The next question is about an industrial press. Okay, we have a press is mounted on a rubber pad. Okay, on a rubber pad. Okay, let's move down. To isolate it from its foundation. So mostly we put some rubber pads to avoid the transmitting of rotating or the vibration into the foundation, right? Avoid crackings and so on. So if we illustrate a drawing, this is, let's say, this is a industrial press, and this one is rubber pad. Okay, so let's say this one. So, and this is the flow. All right. If the rubber pad is compressed 5 millimeters after applying the force over the bed, okay, because of the press, okay. So this one, this center, it was in here, okay, but it become in here about 5 millimeters, okay. So this is the deflection, right? This is the deflection. It was at the center in here, then it become in here. Let's call it X. Find the natural frequency of the system. We need the natural frequency of the system. How can we find that? We don't have the stiffness of the rubber pad. We don't have the mass of the press. Only we have the displacement of the rubber pad. Okay. This one, if you can represent it as spring mass system, right? And that one, so it's going to be compressed about 5 millimeters, okay? So this is, if we represent it as in vibrational oscillational system, become this way. So how can we How can we determine the natural frequency of the system? Anybody knows? In the previous classes, we conducted the how to find the equation of motion, right? Equation of motion for this one. Now, is it moving? Is it displacing? Only we put the press machine over the rubber band. And the rubber band compressed about 5 millimeters. Okay? We don't have any movement, no acceleration. Acceleration is equal to 0. We apply Newton's second law, right? Newton's second law is stating that the summation of all forces acting of the mass, all right, would be equal to mass multiplied by acceleration. Okay? Mass multiplied by acceleration. And the acceleration is equal to 0. It doesn't move. There is no an earthquake. The press machine is not working. It's just supported by the rubber band. Okay? And therefore, the force is over the mass. Okay? Let's make the free body diagram. This is the mass. What force is acting of that? So we have the spring. We'll try to push it this way. This is a spring force, Fs. Okay? And the weight. Okay? And the weight, which is this direction. Okay? And let's call it W, right? Weight. Okay? So, now, let's make the equation of motion. Is there any other forces? Huh? Gravity will be the weight. Okay? Okay. Then how you determine now we have two forces. Let's make it in the formula in the Newton's second law, and that one will be if we assume this direction is positive, then it will be Fs minus W equal to 0. Fs, which is the spring force. Okay, the spring force will be what? So Fs should be equal to W, and Fs is what? How can we calculate the spring force? K multiply the displacement, right? So K, which is the stiffness of the spring, and how much displacement is gonna happen, right? So, and this one will equal to the W. And W is what? Very easy. Yeah. Yeah, by the gravitational acceleration, mg. All right. So normally, if you would like to know the angular frequency, it will be the square root of k over m, isn't it? We don't have k, we don't have m. We have only the displacement, right? Okay, so from here, we can find that, okay? So k over m, right? So if we divide this one by m and divide this one by m, you will get k over m, right? X equal to g. If we divide g by the displacement x, you will get k over m equal to g over x. But k over m is what? It's going to be omega naught squared. If we square both sides, we'll get k over m. So now, we derive a formula by which we can know the angular frequency of the system, all right? And that one will be g over x. Do we know g, which is acceleration gravitational acceleration? And we know x, which is given 5 millimeters, right? Okay? Then it will become, g is 9 point, let me write it in the right, yeah? So it will be 9.81 meter per second squared divided by x, which is 5 millimeter. So we have to make it to convert it to meter, okay? It will be 10 multiply 10 to the power minus 3. So, and that one be meter. So meter with meter will be cancelled, right? Then it will become radians squared per second squared, okay? Radians squared per second squared. Can you try calculating that? Omega naught squared. And how much that one will be. How much is it? 9.8 divided 5 to the power minus 3. That's 9.81 divided by 5. Well, 1962. And that one is omega squared. We didn't find omega, okay, notes yet. So you have to put it under square root, isn't it? Which is 1962 radians per second, all squared, okay? Then omega naught will be square root of 1962, and that one will be what? Around 44.29 radians per second. And that's similar what it's given, which is as answer. So now we found the natural frequency of the system only by the deflection, okay, of the rubber pad. Okay, is it clear? We just have some extra practice, okay, extra practice. Next question. The system is found to vibrate. Yep. I'm going to give you I'm going to send you in the Google Drive, okay? So you don't need to have a picture. Okay, so next, a mass spring system. So we have mass spring system. Do we have damper? We don't know. Until now, we don't know. There is no, okay? Is found to vibrate freely. What does it mean freely? Okay, undamped, not undamped. It's no force. Freely means there is no force applied over that. Okay, no force. At frequency 0.5 hertz means half cycle, okay, per second, or it will take every second half cycle, yes, in a vacuum, right? We have a vacuum in here. So frequency at a vacuum is going to be 0.5 hertz. And when a viscous fluid medium is going to be, so it will be spring mass system, right? Mass spring, okay, which is moving freely, okay, without any force, okay? If we assume this coordinate system to the right, okay, so then sometimes if you apply this one in a vacuum, there is no drag force, okay? No drag force. There is no drag force. You remember Galileo's experiment to check? Huh? Yeah, when he threw the two different masses from the top of the Pisa Tower. Okay, Pisa Tower. Don't know how they wrote it. Pisa. Pisa may be like this. Same like pizza? Or are you hungry, Abdullah? So Pisa Tower, he threw two items with different okay, with different masses, but same shape, all of them, or both, there is a difference in the they reach in different time, okay, but because of the masses, right? Okay, but it's wrong. So it depends on the drag force. It depends on the shape of the material, the viscosity of the air. Okay, so if you bought the feather, okay, if you bought two tubes, if you use two tubes, right, vacuum tubes, right, then if you bought a stone and a feather, okay, both of them in vacuum tubes, they will reach in the same time. All right? It's regardless to the mass of the. It's a mass because if there is no viscosity in here, there is no drag force against. Okay, and the drag force will depend on the shape. Now?
No resistance.
No resistance, right? Both of them they reach in the same time. Okay? Due to the gravitational force, okay? Gravitational acceleration, right? Or the gravitation between the feather or the stone to the ground, okay? Which is 9.81. Then we apply this one in vacuum and we apply it in viscous fluid. Okay? And you will find that in viscous, the frequency will be less, which is 0.45. Okay, 0.45. Find the damping constant. Okay, now they have a damper. The damping constant means the overall, which is the damping due to the presence of viscous fluid in there. Okay, we don't know what's fluid there. Maybe air, maybe steam, maybe glycerin, whatever. Okay, then they will just displace the mass, and it will let it oscillate. Okay, when there is vacuum, 0.5 hertz. When there is viscous fluid, become with a damping which is 0.45. Okay, so find the damping constant, assuming the spring constant is 10 Newton per meter. This is very interesting. How can you do it? You have to apply a formula which we did it in the last class. Firstly, you have to know we have to apply the formula which is the damping frequency, which is this one. Is there any formula in the chapter you studied in the previous classes? Omega d squared. It's going to be this one if you go in chapter 2, page number. Okay, many formulas are there. Okay, you should know which formula you are going to use. If you go page number 26, where's yours? Home? Formula number 2.24. Okay, there is omega d, or n is equal to omega naught, right? Or go to 2.26. Sorry, 2.26. So omega d squared, which is the damped frequency, is equal to omega naught squared to the natural frequency minus gamma squared over 4. Okay, so that one, omega naught squared minus gamma squared over 4. The derivation already given in the previous classes. All right, so we are going to apply that one. So how can we do that? So to solve that problem is by, so for example, gamma is what? C over m. Is the mass is given? No. All right, we need the man. We have the K now. We have the K, we can get the mass. All right? So if we know the K, all right, if we know K and we know the vacuum, right, then we can know omega naught. Omega D is what? We'll go for the viscous. There is damping due to the viscosity. And omega naught will go for a vacuum because there is no damping at all. So omega naught would be square root of K over M. But this one is given, which is omega naught is equal to 2 by F, vacuum. And that one will be 2 multiplied by 0.5 hertz. And what you'll get? Half of 2 is 1, then we'll have by radians per second. It's not squared. Huh? It's not squared. Yes. So you have to square it to get the M. We need M now. All right? We need N. So so if we square this one and this one, then we will have pi squared. All right? Or let me, the M, if you square both sides, what you will get? Omega naught squared equal to K over M. M in here, omega naught go to the other side. Then M will be K over omega naught squared. K is given as 10 Newton per meter. Omega naught is pi squared. Okay? Then you will get the angular frequency in radians per second. It will be 10 divided by pi squared. Okay. What you will get? So the mass will be 1 kilogram? 1.01, yes. 1.01 kilograms. All right? Now? Yeah. So if we would like to know the mass, but if you would like to know omega D, for example, it will be similar like this formula, 2 by F viscous. And that one will be 2 multiplied by pi multiplied by F viscosity, which is 0.45. So omega D is going to be what? 0.45 multiplied by 2, you will get 9 over 10 or 0.9, okay? Which is 0.9 pi radians per second, okay? So we need now gamma, right? Gamma will be what? Okay, if we would like to derive this one, then gamma squared will be omega D squared minus omega naught squared multiplied by 4, isn't it? Then gamma, if you have square root of the both side, left and right side of the equation, you will get the square root 4 omega D squared minus omega naught squared, right? Would be something like this. But square root of in here, what does it mean? It means you will have square root of 4 multiplied by square root of omega D squared minus omega naught squared. And square root of 4 is what? So we will have 2 square root of omega D minus omega naught squared, okay? But remember, gamma is C over M. So M will be in here, and C will be. So we can find the damping now. All right? You don't need. You need to have the M. You put the M. and 2 multiply 1.01 kilograms multiply by 0.9 by squared minus by squared. Minus or plus? So you'll get a negative value in here, isn't it? You'll have a negative value. Sorry, it's the other way around. Sorry. It's the other way around. Why? Nobody. So this one will move to this way, to this location, and this one will go to the other side. So you will get omega naught minus omega d. Okay. You are sleepy or what? So here will be omega naught. I already traveled all the way, okay? But you are just relaxing in the company, no? Oh, the last day of the week. It's not there. All right, then what we'll have? Then by squared minus 0.9 by squared, right? Try to calculate, use your calculator, practice using the calculator, what you will get. You'll get around 2.770 or 50. No, 2.7750. Why? Two divided by it will be 2.7749, which is almost 2.775, okay? 2.775. Okay. And what's the unit in here? Abdullah? What's the unit? Which is the damping coefficient? Or damping constant? Newton second per meter. Okay, you have to remember that. Newton second per meter. All right. Then this is the right answer. What's given in the solution. All right. Is it clear? So now we have this formula. You have to worry about this formula. All right. 2.26 in your chapter 2. Okay. So you have to use this one, okay? Any question until now? We are moving very fast. Yes. Yeah, because gamma is equal to C over M, right? So you make gamma C over M. Then this one will be C over M, right? Yeah, this one C over M. So we multiply both sides by M, then in here would be M. If you multiply this side by M, it will cancel M with M, then you are left with C. So this is the. All right. So I'm going to give you this one. PDF file in the Google Drive. Okay? Let's save some time because We don't have much time. All right, let's move on. Huh? You have a question? What's the wrong? Did you find it? Ah, okay, there is almost. So the wrong, you know the error is what? This is 1.01. 1.01. If you bought instead of 1.01, 10 to over pi squared, and you bought it instead in here, then you will get the same answer. Yes, yes. 2.7750. So what you will get in here, just plug 10 over pi squared instead in here, okay? So you bring this one to replace this one, okay? So you avoid the error in decimals, okay? The error in decimals, that's all. So you have more precise answer later, okay? Try it and let me know later, okay? All right, let's move to question number 4. Question number 4 says a weight of 50 Newton is suspended, okay? So it's kind of suspended on the ceiling. Suspending over the ceiling, we have a mass, okay, which is 50 Newton, right? 50 Newton. Then it's suspended from a spring of stiffness 4,000 Newton per meter and is subjected to harmonic force. So this one is going to move in this direction, and also there is a force in here, which is harmonic force, Ft, which is, and its amplitude is 60 Newton. So the mass, let's write down what we know already. This is the weight, not the mass. The weight is going to be 50 Newton. The spring stiffness is 4,000 Newton per meter. The amplitude of the applied force, F naught, is going to be 60 Newton. And the frequency at which force, which is omega, it's not omega naught, or F, it's not F naught, okay? F naught is a natural, but this is F due to the applied force or driving force. 6 hertz. 6 hertz, okay? Now find the extension of the spring due to suspended weight, okay? Due to suspended weight. They didn't mention the applied force until now. So let's try doing that using only the suspended. Let's write it. Answer A would be as a suspended, or the suspended due to weight. What you will get? So you have to make the free body diagram of the system. This is the mass, right? As the mass is pulled down by its weight, okay, there is a force which is a spring force, which is Fs, right? We don't have any normal force in here because it's not landing over the foundation, okay? So it will be only hanged in here, okay? So as this one trying to move in here to downward, which is in the positive direction, we assume it's a downward positive direction, then the spring will try to pull it up, okay? There's a tensile, a potential inside the spring, okay? Opposite to that one. So now we applied Newton's second law. Summation of all forces would be equal to mass multiplied by acceleration. Acceleration positive if it's going to down, okay, toward down, okay. So the summation of forces, positive is W, all right, and negative is the spring force. W minus Fs is equal to mass multiplied by acceleration, okay. So, and W is what? Mass multiplied by angular, gravitational acceleration minus kx, kx, which is the spring force, equal to mass multiply acceleration. Is it if it's only by, it's not freely applied, it's not oscillating, it's only by the weight, what you will get the acceleration? 0. So that one, acceleration is going to be equal to 0. Therefore, this one will be equal to 0. Then what they want to know? They would like to know the displacement, isn't it? So the displacement, which term in this formula? X. And X, if we move this one to the right, and mg in the left, okay, what you get? Mg, okay, X is going to be mg over k. And mg is given, isn't it? Which is 60 Newton. And k, is it given? 4,000. That's 50, sorry. Yeah, it's already given. The weight, mg is the weight. Okay? So we don't know the mass. Is it given mass? There is no mass. Only they give us the weight. Already, the force is given. So it will be 50 divided by 4,000 Newton per meter. N with N will be cancelled. Then it will be in meter. Yeah, but it's already the weight. They give us the weight. They didn't give us the mass. Huh? So the weight is the force already. So 50 divided by 4,000, what you will get? Will be 0.0125, isn't it? What? Meter. Okay, so this is the answer of the first part of this question. The second part, the amplitude of the forced motion of the weight. No? The static displacement of the spring due to maximum applied force. The static displacement. What does it mean, static displacement? Previous class we discussed about the static displacement. Yeah. When omega is approaching what? Maximum? Is it approaching infinity, approaching the resonance, which is omega naught, or the equal to the 0, approaching 0? It's going to be 0. While it's going to approaching 0, then the amplitude of oscillation, okay, which is the maximum displacement, is going to be equal to F naught over K. Okay, F naught over K. So you have to remember static, okay, static displacement or static frequency. Okay, so this is very important for you. What resonance means? This is already you have studied in the last year. Okay, the resonance. Okay. This year? Yeah, it was this year. Yes, it was in March 2019. Okay, so last semester. But you went for vacation for summer. Now, maybe you forgot about. Huh? All right. Okay, so for B, what you are going to do for B is if we think about static, it means we are going to apply the driving force in the formula, okay? Let's do part P. Part P is going to be, you have to put the free body diagram again, and that one be in here, will be the applied force. Once you apply force, then that one will be more than the weight, okay? More than the weight. And the question said static frequency or static displacement means because of the driving force, okay? because of the driving force, and also there is a spring force all the time, okay, Fs in it. So we applied Newton's second law, the equation of motion, it will be, so now if we say there is static, means the acceleration will be 0. Why? Because the speed or rate will be, speed rate is going to be equal to 0, okay? So as you see it as stopped, okay? You can see it as stagnant, okay, in the air, okay? But that's the static, they call it the static. That's when once you have the rotating machines, right? When you started the machine, then you will have a big displacement, right? After that, then it will come vibrating. It's vibrating, but you don't see it vibrate. It's like static, means omega is almost approaching 0, right? Then the acceleration is equal to 0. So what you will have in here in the formula, we have the force minus kx equal to, the acceleration is 0, then this one become equal to 0. Then we have the formula as this way. What they need to know, the displacement, isn't it? So if we get the displacement in the right, and that one be F naught over K, and this is, you have to remember this formula. When we say it's static, okay, displacement, then it will be X equal to F naught over K. Why? Why? If you go page number, or if you know the general formula, okay? The general formula is the amplitude is equal to F naught over K minus omega squared, right? As omega is going to be 0, then we are left with F naught over K. It's not 0. So this is 0, but we have K in here. If omega is approaching infinity, then the amplitude is going to be 0, right? But if omega is approaching omega naught, which is the natural frequency, then the amplitude is the maximum, right? You remember the resonance? If the applied force frequency is equal to the natural frequency of the system, then we have the maximum, which is the peak of the displacement, right? So the theory is correct. So F naught X equal to F naught over K, and that one will be equal to what? So we know F naught. How much is 60 Newton? And this one is 4,000. 0 is 0. Then 2 will be 200, and this one 3. 3 over 200. What you will get? You will get around 0.015 meter. Okay. So this is the answer of this part of this question. All right. Then let's move on. So what they need to know again, this is a long question, 3 parts. The amplitude of the force motion of the weight, okay? Now we apply force and we have to include the weight in there. We have to include the weight, right? We don't have damping, okay? This formula is we don't have damping, so this formula is only applicable to free forced oscillation, right? I mean, forced and damped oscillation, or forced and damped oscillation. So the amplitude of forced motion of the weight, right? We have to apply this formula. Can we apply this formula now? Yes. What we are missing this formula to find? Okay? We apply this one for the forced weight, okay, of the force, the displacement, or the amplitude of displacement for the force weight. Okay? The force is given, K is given. Omega, how can you find omega? From the frequency. Frequency is how much? 6 hertz. So omega how much? Make sure that it's not the natural, okay? What they said in here. And frequency means the frequency of driving force. It's not the natural frequency. So omega is going to be what? Omega is going to be 2 by F, isn't it? So it will be 2 multiply, F is 6 multiplied by, and that one will be 12 hertz. Hertz? Radians per second. So good. So we have radians per second. All right. Now we plug omega in this equation, then the maximum or the amplitude will be given. Now A will be F naught is 60 divided 4,000 minus 12 by, sorry. 12 by whole squared. Now your eyes are open. So can you calculate that? So you practice using calculator every time I come. You bring your calculator with you guys. So because we have limited time in the exam, and the squared because already omega squared in here. So we have 12 by squared, right? How much you will get? No? Sorry, it's not. So the amplitude, maybe it's going to be negative, maybe it's going to be positive. Okay, both will be okay. Because the amplitude means if either to have minimum or positive or negative, which is that. You remember a circle, huh? No. 185, isn't it? So it would be minus 0.0185. Okay, and that one will be meter. So means it's the amplitude is going to be 0.0185. Okay, which is the just maximum, or this is the absolute value will be this one. Okay, this is the answer of that one. All right. Now we applied 3 ways. 3 questions and
the answer is 130 minus
no, yeah, it will be positive, okay? So if it comes in negative, okay, all right. So now we are talking about oscillation, right? If this one is moving up and down, right? It's oscillating. What will happen? It will be represented in a circular motion, okay? Assume this is a circle. Okay, sorry for the bad drawings. So if we represent the oscillation, we can represent it as a cycle. So it starts in here, 0 displacement. It will go to the top, okay? So if you have this point in here moving, all right? Okay, and it moves at frequency omega due to the force. Then the amplitude positive in here, and it will be the amplitude negative in here. And this is going to be 0. So either positive or negative. But remember, if you are going to, if you are sure about your answer and you put in the online test negative and it doesn't work, you should make it as a positive. So you have 2 attempts. But if you are sure about the answer, then make sure that you correct it. Instead of negative, it's going to be positive. And you have to take care of decimal places. Okay, decimal places. Clear, Khamis? So this one will be, they said, if they calculate it, it's going to be 0.01. كم؟ ليش ما طلعت؟ 12 by squared, both squared. So it will be 144. 144 multiply 3.5. How much you'll get? Oh. Sorry, we forget about in the formula, which is in page number, will be page number 19, formula 2.12. Sorry, this one will be, what you will see? You will see mass multiplied by, okay. What's that? It's going to be m omega squared, okay? So this is what I missed in here, sorry. And that one will be m. How much is m? M is given. Again, we'll find, oh my God. Can we find that? Can we find m? Where is it given, the weight? It's going, yeah, they give us 60 or 50? 60? 50 or 60? Yeah, 50 is going to be 50, yeah. So the weight is 50 divided by 9.81. So we 50 divided by 9.81. And the mass is not squared, but omega is squared. Multiply by 12 by all squared. Now we try. Good, that you are trying. That means you understand why positive or negative.
Because what we get now is minus, right? Negative. Why do you change it to negative?
It's either both are correct. Both are correct. Why? Because it's going to be minus 0.0185. Good that you. Or 0.0185. This is the amplitude. Either it's going to be negative or positive. Yeah. So you have maximum forward or maximum backward. Okay. So this is the displacement. Okay, Mana? All right. Yes. Now it's clear.